We have four talks today. The first talk is entitled Technical Meeting Authenticated Encryption, joint work between Mihir Belare and Viet Long Huang, and Viet Long will give the talk.
Thanks a lot, Bart, for the introduction. So, symmetric encryption is a fundamental primitive in cryptography. So, in fact, for ordinary folks, cryptography is just symmetric encryption. But over the time, this primitive has evolved. So, for classical encryption like CBC or counter, they only provide privacy. But after several devastating attacks, now major network protocols like TOS only use authenticated encryption or AE that provide both privacy and authenticity. And for a while, that works pretty well in practice. But lately, attacks shows that privacy and authenticity are no longer enough. For many emerging applications like Facebook's message banking, Amazon's cloud encryption, they all demand a new type of security that we call committing security. And there are several flavors of committing security, but in this talk, we will use a notion in our Eurocrypt 22 paper because it's simple and because it's optimally strong. Now, intuitively, committing security means that it's hard for the adversary to produce a self-text collision. At the first glance, it seems to be a very natural requirement for encryption, but attack shows that popular AE schemes like GCM or CCM, they are all broken under this notion. On hindsight, it's not surprising. Modern encryption schemes are very highly optimized. So if you pick a non-desired goal like committing security, it's not likely that they will support that. So because of this situation, lately there have been several committing AE designs from both the industry and academia. So it turns out that if you are happy with 64-bit committing security, also known as versatile security, then we can offer something as close to GCM in both speed and bandwidth. But in this setting, we actually want at least 80-bit securities because attacks here are offline like hash function. And preferably, we want 128 bits of security. And if you want that strong security, then contemporary committing AE schemes need to use more bandwidth than GCM. In particular, let's look at the ciphertext expansion, namely the difference between the ciphertext length and the message length. For GCM, it only uses 16-byte expansion, but for other committing AE schemes, they need at least 32-byte expansion. And the goal of our work in a nutshell is to get back into a 16-byte expansion, but at the same time, provide 128-bit of committing security. Now you may wonder, what's the point? The gain seems to be pretty little, just 16 bytes in the bandwidth. Well, the answer is that having a big expansion can be very undesirable in some settings. For example, if you have some legacy software, then you may have trouble because the norm there is to have 16-byte expansion. Or in router applications, they even want shorter expansion to minimize the bandwidth. And in energy-constrained environments like IoT, it's critical that you use a short expansion to save the energy. So I hope that in this point, you would agree with me that sharing up 16 bytes in expansion is a worthwhile goal. But at the first glance, this goal seems to be doomed, even if you just encrypt the empty message. In particular, regardless of how you design your encryption scheme, that's a simple bursting attack. The adversary simply pick several triples of key, nonce, and AD, and then try to encrypt them with the empty message to fire a collision. So the apparent conclusion here is that if you settle for tau-bit expansion, at best you can hope is to get tau over 2-bit of committing security. So pictorially, You cannot hope to get into the shaded area, at least unconditionally. So a concurrent work by Nato, Sasaki, and Sugawara show how to bypass impossibility by assuming that the message has enough redundancy, and this redundancy must be known to the encryption algorithm. So of course, if you have that one, you can do some compression and so on, and it might work for some niche applications. But overall, it is a very restricted assumption, and we instead opt to achieve the goal for general message space. And in order to do that, we need to look at the birthday attack to see what it actually means. So the birthday attack doesn't say anything directly about the expansion. It only says that the ciphertext length needs to be at least 32 bytes. This, however, translates to a requirement on the expansion because firework implicitly assume that the expansion must be constant for all the message length. And to avoid this impossibility, one direction is to use variable expansion. That is, if your message is empty, sure, you have to use 32-byte expansion because of the birthday attack. But as long as your message is big enough, the eventual expansion can be just 16 bytes, the same as GCM. Now, this gives us a way out, but it's unclear how to get to the goal, let alone finding a practical solution. Not because the gap between the solution is kind of large, so I would break that into two steps. First, I will show how to get 128-bit committing security very quickly, even if we have to pay the price for a 32-byte expansion. In particular, we build a citywide transform that turns a standard AE scheme into a committing AE of 32-byte expansion. And the overhead here is the hashing of the AD, which is inherent. Now, this transform requires that the standard AE to be tag-based, a property held by the popular AE schemes like GCM or CCM. Now, based on this, we already have a good committing AE scheme. The performance is optimal, but the ciphertext is large, so we need to shorten it, but at the same time, preserve the committing strength. Now, in particular, we build an SC transform that turns our committing AE scheme into a succinctly committing one, namely that the expansion would be 16 bytes once the message is larger than 16 bytes. And the cost of this transform is very cheap, just 2 AES calls. The transform demands a little bit more about authenticity than usual, but this property is met by citywide anyway, so not a big deal. So now, guided by this roadmap, let me show you how to get to the committing security very quickly. And as a warm-up, let's revisit the CTX transform of Channel Railway. So in this transform, you will first encrypt as usual to get a tag T and a ciphertext score C. You then hash the key K, the nonce N, the ADA with a tag to get a synthetic tag R. And finally, your ciphertext will be CR. This transform works because obviously KNA is committed, and the message is also committed thanks to the correctness of the encryption algorithm. So while the CTX transform is simple and elegant, it is, however, not optimal. In particular, the AD is processed twice, one by the encryption scheme and another by the hash function. And to remove this redundancy in our citywide transform, we simply encrypt with the anti-AD. And this time, the overhead is theoretically optimal. So in practice, the AD may be pretty short. It's most likely to be a packet header. So what is the gain here? How important is the improvement? So experimentally, even if the AD is relatively short, say 5 bytes, you have appreciable difference between CTX and CTY, like 5% for small data. So now we have a good committing A scheme, CTY, but we don't like the ciphertext size. We need to compress that. And in order to do that, I introduced a new tool that we call invertible PIF, or IPF for short. So IPF is basically a PIF, as the name suggests, it's invertible. So think of it as a generalization of a block cipher. But at the same time, to have committing security, we want that IPF to have collision resistance as well. So now if you look at the collision resistant IPF and committing AE, similar problems. So why would we opt to deal with one problem first before the other? The answer is that if we choose the domain and range for the IPF wisely, then it will be a much easier problem to deal with, and it will give us some stepping stone in solving our ultimate problem. In particular, let me give you some intuitive clue on why it's an easier problem. Now, for committing AE, you have to deal with nonce and AD, but there's no such thing on IPF. On committing AE, you have to deal with messages of any length. But on the IPF, we will only aim to deal with very short messages. And that makes it a lot easier if you want to build things from AES. For succinctly committing AE, your ciphertext length is a complex formula. But for IPF, we would aim so that the ciphertext length is a constant. Now, I will show you later how to build the IPF. For now, let's see how to use that in our SC transform. So in the transform, we break the message into a prefix P and a suffix S. The suffix should be as large as possible, but only up to 16 bytes. Now, that is, if your message is very short, S can be your entire message. But if your message is long, then S is only 16 bytes. Now, once we do that, we would first use our base committing A scheme to encrypt P to get a tag T and a ciphertext score C. We then use the IPF to encrypt S with T as the key, and that produces a synthetic tag R. And finally, our ciphertext is CR. Now, what is the expansion? So the expansion here is the gap between the length of R and S. And if your message is big enough, then that is only 16 bytes. And the ST transform preserves the committing security of the base A scheme, provided that the IPF is also collision resistant. And to see why it's true, note that for committing security, we want to commit KNAPS. So we first use the committing A to commit that into CTS. And then we commit that again by the IPF to get CNR. So ultimately, after a chain of hashing, we get the CR is a commitment of KNAPS. So we see that the IPF would help us to solve the problem. But how would we do that in the first place? It turns out that the IPF is not something new. It is actually a special case of pseudo-random injection. And you may better know that by the name of misuse-resistant AE. And based on the existing way to construct misuse-resistant AE, so there are two paradigms to construct the IPF, namely the encode and encipher paradigm, or SIV. And I will show you how to use both ways to build IPF. So to use the encode and encipher paradigm, you would pass the message up to 32 bytes and then encipher that with a block cipher. If you model the block cipher as an ideal cipher, then that would have 128 bit of collision resistance. But the block cipher now has to have 32 byte block length. So you cannot use AES for that purpose. Instead, you have to settle with something like radio 26. Now, let's see how to use the SIV paradigm to build the IPF. So here, you first need to pass the message up to 16 bytes, and you hash it to get a tag T. You then hash the tag again to get a one-time path to encrypt the private message. And on instantiation, we'll build the hash functions from the Davis-Meyer compression function. And this time, the block cipher can be AES. If you model the block cipher as an ideal cipher, and the tag length is lambda bits, then you have nearly lambda bits of collision resistance. And lambda is not 128 bits because we need to pass the tag for domain separation, but it is close. So overall, the collision resistance is nearly 128 bits. Now, if you have a second look and say, wait a second, seems to be suspicious, the tag is very short. So why can an adversary launch a birthday attack to have a tag collision and so on? So the answer is that our result relies on a circularity between the message and the tag. You hash the message to get a tag, but at the same time, you hash the tag to mask the message. So if you simply launch a birthday attack, then you can have a tag collision, sure. But at the same time, your ciphertext won't match entirely. But to exploit this intuition, your hash functions must be somewhat an ideal primitive, like a random oracle, or in our work, Davis-Meyer with an ideal cipher. Well, the proof is actually very complicated. In construction, you hash M first to get the tag, and then you hash the tag and so on. But in adversary queries, you can make out-of-order queries. Besides, the hash functions are built on a block cipher, so adversary can make forward and backward queries. So that can be really a mess. So we, in fact, have to use a tedious case analysis on how the adversary makes queries. Naively, there are just too many. But by doing some little tricks, we can prune that down to about a dozen of cases, which is practical. And we show that in each particular case, despite all the adaptiveness and so on, the adversary implicitly plays a game of balls into beans. So by doing some concentration, we can show that it doesn't fare much better than the naive strategy. So in conclusion, we believe based on time that we should have committing a standard. If you look at the situation, it's like ad hoc because many applications want committing security, but each ends up with its own suboptimal scheme. And this gap saturation won't happen if we have a standard. And our schemes here can serve as a first starting choice. Thank you.
Very much. Any questions?
Thanks for the talk. I was wondering, you're in your ciphertext shortening transform, you're using the tag from the AE scheme as the key for the IPF, correct?
Yes.
Do you need some special assumption on the pseudo-randomness of that tag in order to be able to use it as a key?
Yes, so that's what I mentioned, that we need stronger probability from the authenticity than usual. So the tag here needs to be used as the key. So you cannot simply plug an arbitrary AE scheme there. But overall, because in our transform, the tag is obtained by hashing the ID and so on. So it's more like a random oracle things. So that's why it can be used as a key.
I see. So it's part of this proof of how what your assumptions you're making.
Yes. So we have to give a dedicated proof that the CPY construction actually works with this transform. Yeah. So that so committing security, it can work generically, but for the standard AE schemes, you need a dedicated proof for specific construction.
Thank you.
Did you look at the performance? Do you have a guess for the performance cost of going to this committing encryption?
Yes, so we actually have some little experiments. And so let's see, I have some, oops. May I have the slides back? So here, if you just care for, okay, let's see that. Let's see where's, okay, here it is. Oops. Okay, here. So if you just care to get the committing security, but ignore the expansion, then yeah, so that is the data. So, and that is theoretically optimal because the hashing is very slow compared to AES. So there's a discrepancy between the hashing cost, the speed, and the AES speed. And now it will be a little bit worse when you add all the IPF there. That will make about probably 10–15% worse in the performance. Yeah, for the small data. But of course, on the long run, then you get the constant overhead. So that would be negligible in the long run.
Okay, let's thank Viet Tung again. Thank you very much. So we move to the second talk of this session. It's entitled Tight Factorization for Preprocessing Against Cryptographic Sorting. It's joint work between Fangxi Dong, Qipeng Liu, and Keiwen Wu.
You want to put it
Fangxi will
Clip it to
give
your
the
pocket
talk.
or whatever.
So,
That's forward and that's the laser.
uh, okay.
There we go.
Um, Thanks for the introduction. This is a joint work with Qipeng Liu and Keiwen Wu. In this talk, we focus on cryptography hash function. It denoted as H from M to N. When we care about the security of hash function, actually we care about the specific hardness of the underlying cryptography primitives. For example, one-way function refers to the hardness of finding primitives of designated output, and collision-resistant hash function refers to the hardness of finding a pair of collisions that has the same output. In the random oracle model, well, the hash function is modeled as a black box random function. We can easily characterize the security. That is, it requires roughly theta n queries to the hash function to find an image, and it requires about square root of n queries to the hash function to find a pair of collision. This is all under the lens of uniform security, where the capability of the adversary is assumed to be fixed and oblivious to the actual primitive, the hash function. However, this fails to capture some more practical attack like preprocessing adversary. For example, an adversary might perform extensive interactions with the hash function SHA-3 with significant amount of computational power and time in some offline phase. Then it can just store some advice. In the online phase, it will receive a challenge, and he can use this advice to solve that challenge. In this case, with this offline preprocessing phase, the adversary can sometimes perform much better. One example is for the collision finding. If the adversary reads through the truth table of SHA-3 and store a pair of collisions in its advice, it might just output the answer in the online phase and always win with probability 1. So this kind of preprocessing collision finding becomes trivial for the adversary. So how can we save some security against this kind of preprocessing adversary? A universal and fundamental strategy is called sorting. That is to include a random value as a sort in the input. Now the adversary needs now the output of hash function additionally relies on this input sort, which is only randomly sampled and given to the adversary in the online phase. We still take collision finding as an example. Now the adversary will have access to this sorted SHA-3 or this sorted hash function, and it can preprocess for a long time and store an S-bit advice. In the online phase, it will first receive a challenge, which is a randomly sampled sort sampled from the source space capital K. Then for this collision finding problem, it needs to output a pair of collision that is on this sort, which is a pair of x and x prime such that hkx equals to hkx prime. One intuition is that as long as the adversary cannot store answers, store collisions of all sorts in this short advice, the randomness of this challenge sort K might prevent the adversary from the most trivial attack and might force that adversary to perform significant computation in the online phase. Sorting is first introduced by Morris and Thompson in 1979, and there are a sequence of works after that. Recently, Coretti, Dode, Score, and Steinberger show that sorting generically defeats preprocessing. They care about cryptography game denoted as G in the random oracle model. Here we denote epsilon GT as the maximum winning probability for a T-query adversary without preprocessing. GK is the sorted version of the game, which is for the assorted random oracle model. And we denote this epsilon GKST as the maximum winning probability for an online T-query adversary that has already preprocessed an S-bit advice in the offline phase. In their work, they gave an upper bound for this non-uniform security, which is upper bound by this epsilon GT plus ST over K. The first term is for the uniform security, and the second term is for the preprocessing advantage. In the context of collision finding, the uniform security is T squared over N, which is just like it is achieved by the birthday attack. And this preprocessing advantage upper bound shows that an S-bit advice might give an advantage no larger than ST over K. This will decrease exponentially when the number of bits of the sort increases. But this fails to match the most intuitive attack. For example, an optimal adversary might do the following attack. That is, it just stores collisions about S sorts in its advice, and then in the online phase, it either looks up from its advice or performs the birthday attack. This will only give a preprocessing advantage of S over K, which is for the case that the challenge sort is sampled from the sorts that adversary has already prepared in its advice. So there's a gap between the previous best advantage upper bound and the most intuitive attack. We also care about more powerful adversary, about quantum adversary. Previously, there are some results for games in the quantum random oracle model, where the adversary can make superposition queries to the hash function. Here we use star to denote the quantum case. Chong, Guo, Liu, and Qian show the similar results of ST over K for quantum adversary with classical advice. And later, Liu showed a similar result of ST over K for quantum adversary with quantum advice. That is, now the advice is a quantum state of S qubits. You see, this is ST over K, so it still fails to match the most intuitive attack, S over K. Based on these gaps, we ask the following question. Can we provide tighter characterizations for preprocessing against sorting in both the classical and the quantum world? We give several results for this problem. First, in the classical setting, we give a tighter characterizations for preprocessing for any gains in any idealized model. We also get a tight bound for sorted collision finding that matches the most intuitive attack. That is, the preprocessing advantage is just S over K. We also develop a framework for game with challenges. That is, a challenge will be sampled together with a sort and given to the adversary in the online phase, just like function inversion, when you will need to sample a challenge, which is the image. In this setting, we reprove the previous best bound for sorted function inversion, and we also get a tight bound for many gains for the case when the size of the device is quite large. We also care about the quantum case, that we get a tighter bound in the quantum random oracle model for a special set of games which we call property finding games. Collision finding is one of them. So we also get a tight bound for sorted collision finding that matches the most intuitive attack, even against preprocessing quantum adversary with quantum advice. Here's an overview of our results. First, for the classical setting, we prove a tighter bound for any cryptography game in any idealized model. That is, we tighten this non-uniform security with a preprocessing advantage no larger than S over K, removing the previous T factor. This is tight for a game without challenges, just like collision finding. this best preprocessing advantage is just achieved by the most intuitive attack that is just store answers for S sorts and run the uniform algorithm for the other sorts. Apart from the tightness, our result works in any idealized model, including random oracle model, random permutation model, or any distribution of oracles. We also have very clear lower order term here, with just a constant factor of 2 compared to the previous result. So actually, our result can handle very small regimes of SDK and might be useful for some analysis in practice. Following from the proof of our first result, we also obtain a corollary for game with challenges. That is, now a challenge will be sampled together with a sort and given to the adversary in the online phase. So if the adversary cannot store answers for every challenges within one sort in very short advice, this might lead to an even smaller preprocessing advantage, maybe much smaller than SOK. In this setting, we reproved the previous best bound for salty function inversion in the random oracle model, where the preprocessing advantage is STOKN. And this result shows that preprocessing will not give you any advantage as long as your advice size is not as large as a source space. We also give a tight bound for many games for the case when the advice size is as large as a source space. In this case, the non-uniform security will match the following attack. That is, the best thing an adversary can do is like, it just partitions the advice for each sort. That is, he prepares advice for each sort. And then in the online phase, when he receives a challenge sort, it just uses the corresponding advice to solve that. So in this sense, our bound is tight in this way. Then for our quantum setting, we get a tighter bound in the quantum random oracle model for a special set of games which we call property finding games. This set of games are some games without challenges, and that includes zero preimage finding, collision finding, k-sum, and so on. Specifically for this sorted collision finding, we give an upper bound for this non-uniform security, which is T cube over n plus S over k. This T cube over n actually comes from the uniform security of quantum collision finding, and it is achieved by the quantum collision finding algorithm, the BHD algorithm. And the preprocessing advantage term, S over k here, it is tight because it matches the most intuitive attack, which is just to store collisions of S sorts, even for quantum adversary, even for quantum advice. And here are some main ideas about our proof. First, for the classical case, we follow the previous method, which is to reduce the non-uniform security to some multi-instance game. For a multi-instance game, the adversary will receive a set of instances, for example, a set of sorts, and then he can queries to these hash functions and gives answers on these sorts. For example, now it needs to answer different collections on the different sorts. But here, we made a slightly difference. That is, we reduce our non-uniform security to some memories multi-instance game. This memory structure is like the adversary will receive instances in different rounds. Each round, it will receive an independently sampled instance. After it queries the hash function and gives answer on this instance, it can only enter the next round after it clears its own memory. So the adversary will not share any working memory between different rounds. Actually, this reduction is done by Jensen's inequality. So we can actually reduce this non-uniform security, denoted as epsilon, to some uniform multi-instance security, denoted as eta, where we can get a bound of 2 times eta to the power of 1 over s, while s is the number of rounds for this memoryless multi-instance game. The second step is like we apply a strong direct product theorem for this memoryless multi-instance game. The intuition of a strong direct product theorem is like if the maximum winning probability is delta for an adversary to solve one instance with T queries, then maybe solving k distinct instances with KT queries can achieve a winning probability not larger than delta to the power of k. But strong direct product theorem is not always the case. But for our memories algorithm, we can have this strong direct product theorem. And it is a result in a paper by Nissen, Rudik, and Sachs. There's also one thing to notice is that the strong direct product theorem works for distinct instances, while the memories multi-instance scheme, it's like each instance will be independently sampled and there might be some repetitions. So in our bound, we only look at the distinct set of instances, which is a distinct set of sorts that is sampled in this memories multi-instance scheme, so that we can actually apply our direct product theorem. And this pre-processing advantage, this SLK here, this SLK term here, actually comes from this expectation over this distinct set. Combining these two steps, we can get our upper bound for the non-uniform security, while the pre-processing advantage is tight, which is upper bounded by S over K, matches the most intuitive attack for sorted collision finding. For our quantum results, we try to follow the similar framework in our classical result, but it is generally hard to prove a quantum direct product theorem. So we only analyze some more structured games like property finding games, which includes collision finding games. Also, now we need to handle superposition queries, so we apply Jenge's compressed oracle technique to handle these QROM queries. And we get two results from that. The first result is a direct product theorem for property finding games within the compressed oracle framework. This is also the first average case direct product theorem for quantum query algorithm. For our second result, we try to lift this direct product theorem to the actual non-uniform security that we want for this pre-processing advantage. And this is done by a result in Liu's paper so that we can actually deal with quantum advice. And that's how we get a tight bound for this pre-processing advantage against quantum adversary with quantum advice. And here are some takeaways about our results. That is, sorting generically defeats pre-processing. And this advantage is upper bounded by S over K. Specifically, you can see for collision finding, the best strategy for non-uniform attackers is just to store collisions for a set of sorts in the advice. So we are happy to see that the adversary cannot do much things. It is like the most intuitive attack is already the best for them, for sorted collision finding, both classically and quantumly. And that's all. Thank you.
Thank you very much. Any questions for Fangchi? So maybe let me ask something. You still have this factor 2. You think it's inherent to your proof technique, or it can still be reduced?
Thanks for the question. This factor of 2, maybe it's okay. This factor of 2 is inherently in our proof because it's like when we reduce from the non-uniform security to the uniform security, we try to guess its advice, which will be a price of 2 to the minus s. But we try to amortize that by this multi-instance scheme, which is like we raise to a power of s. So there's a constant 2 there, and it is inherent in our proof.
Okay, there's no further questions. Let's thank the speaker again. Thank you very much. So we move to the third talk in our session, moving back to committing security. The paper is entitled "The Committing Security of Max with Applications to Generate Composition." Joint work between Witan Baumik, Vishwajit Chakraborty, Wonseok Choi, Avir Dutta, Jerome Govindan, Yaobin Shen, and Jerome will give the talk.
So thank you for the introduction. So in this work, we revisit the security of max and generate composition in the context of committing security. So committing security essentially means that it is hard to produce a ciphertext that is valid for two different users. Or said differently, to produce a ciphertext that is valid for two different keys. This is a notion that originates from the public key encryption literature that was then adapted to symmetric primitives with the latest research focusing on authenticated encryption with associated data, or AED for short. So the findings were that there's multiple practical settings that are vulnerable to committing attacks. With, to give a few examples, moderation in encrypted messaging apps, such as in Facebook Messenger, or key rotation mechanisms. In addition to that, looking now at the security of concrete AED schemes, almost all of them were found vulnerable to committing attacks. But what about MACs? So a message authentication code, or MAC for short, is a primitive that provides only authentication. In its nonce-based form, it takes as input a key K, a nonce N, and a message M to return a tag T. There's a wide variety of standards for MACs that are based on different underlying primitives. These are also used in a wide variety of settings. However, despite this wide usage, the committing security of MACs have been scarcely studied. And in this work, we remedy the state of affairs, starting by looking for some practical settings that require some form of committing security. This allows us to identify which security notions are useful to define and analyze. We found out then 4 practical settings, among which only one explicitly stating this committing requirement. The remaining 3 implicitly assuming it to be guaranteed by the underlying MAC. So the first setting we consider is opaque, which is the one explicitly stating its requirements. So opaque is a password authenticated key exchange that is recommended by the CFRG for usage in ITF protocols. And in its original proposal, opaque required its underlying authenticated encryption, or EAD, to satisfy a property called random key robustness. However, in its latest draft, this requirement was replaced by a requirement now on its MAC, which states that given two random keys K1, K2, it is hard to find a message M for which the evaluation of the MAC for this message M under the 2 different keys collide. From possible instantiation for this MAC, they proposed HMAC. So in our paper, we capture this property into a slightly stronger notion we call key committing security. And as our analysis will show, we're able to provide more efficient instantiation of MACs that provide this property. So the second practical settings we look into is key derivation function. So HMAC, CMAC, and KMAC are 3 message authentication codes that are recommended by NIST for sub-key derivation. So how does it work? To derive a sub-key K out from a master key K in, this master key K in is given as input to a MAC attached to a context CTX. This context allows the derivation of multiple sub-keys from a single master key. So this context could contain data such as the purpose of the derived sub-keys, or also other information such as the identity of the different parties using this sub-key. This could also contain a nonce, for example, to prevent reuse. So the NIST special publication 800-108 then recommend adding such context, as it would provide insurance that if the parties have different understandings of how to compute this context, then they would derive different keys. However, such a property is not guaranteed by the standard MAC security. Thus, we capture this property into a new security notion we call MAC context committing security. And as our analysis will later show, CMAC, which is one of the recommended algorithms, is in fact not context committing. So another setting we look into, which now requires not really committing security, but more a related notion to committing security, is Tesla. So Tesla is a protocol that provides sender authentication for multicast and broadcast stream, and is defined in RFC 4082. So to do this, it uses a one-way chain. And how this chain is built, it's first select randomly the last element of the chain, so here KL plus 1, and then apply a function f repeatedly to generate the full chain. The elements of the chain are then revealed in the inverse order of this chain here. So how the function f is defined as follows. So the input to the function f is given as key to a message authentication code attached to a 0 message. And then essential to the security of the protocol here is the one-wayness property of the function f. However, as f is instantiated with a MAC, this is not a property provided by a MAC. Therefore, we again define a new security notion to capture this notion, to capture this property, which is called MAC context discovery security. So from all these practical settings we found, we then formalize this notion, which was required. So we define a key committing attack, or a committing attack, as finding two tuples of inputs for which the corresponding outputs collide. It is then possible to define different granularity of notions, depending on the requirements on the input. So one of them could be CMTK, where the key is different. Or another one, which is CMT, where the whole tuples of inputs is different. So the first one is also called key commitment, and the second one, context commitment. Similar notions exist for AED, where the AED now has an extra input, which is A for the associated data. And instead of a tag T, it returns a ciphertext C, which contains an encryption of the message M. Then key commitment is defined similarly as the key being different, whereas context commitment, the second one, CMT, is a bit different. So it doesn't require the whole tuples of inputs to be different. It requires only the first three elements to be different. And this is a notion that was introduced by Bellary and Huang, and is also called CMT1 or CMT3. So the second notion that was required by our practical settings is context discovery security. So this is a notion that we adapted to MAC, but that was that comes from context discovery notions for AED, which was defined by Manda et al., and is similar to the concept of pre-image resistance for hash function. So it is parameterized by a context selector S, which is a randomized algorithm that returns a challenge value T that is given to the adversary. The adversary then needs to find the corresponding input value that to the MAC that gives them back this value T. So you could like see this context selector as a parameter that allows to model different scenarios, meaning different ways this value T would be computed in a protocol, for example. So in our paper, we also define other weaker security notions and then show how they relate to each other. But as there was no strictly stronger security notion, we've combined the context commitment notion and the context discovery notion into an all-in-one and more compact notion we call strong committing security. And we believe that designers of message authentication code should aim for this notion. So we now have all these notions, and then we analyzed them for several MAC standards. And the summary of this analysis is that almost all of them are broken. So for committing and context discovery attack. So we give a key committing fix for CMAC and its related CBCMAC. And the only one that we found that was context committing is HMAC, whose security follows from its indifferentiability. So to give an example of one of these attacks, you can take a look at CMAC, which is a single key message authentication code, which derives two keys, K1 and K2, to indicate whether the message authenticated is a full block message or not. And then this is stored here. So at its core, it uses CBCMAC, where each message block are fed to a block cipher after being sold to the output of the previous block cipher call. Then the value of the MAC is then the output of the last block cipher call. So we found a key committing attack on these types of MACs, and to roughly describe it here with 3 blocks. So you can choose arbitrary values for the message block M1, M2, M3, and also an arbitrary value for the key K. And then you compute the MAC to obtain a tag T. You then need to find another tuple of inputs for which the corresponding output collide. And for this, you just have to choose arbitrary values for M1 prime and M2 prime here. And then for the key K prime, you choose a different key K prime from the key chosen on the left. And then you just apply the inverse of a block cipher for the value T that you obtain on the left, and you obtain a value M3 prime. This then gives you 2 tuples of input for which the application of the MAC for 2 different keys collides, and it's thus a key committing attack. So we then give a fix to this MAC, which is inspired by the fix for GCM from Bellaray and Huang, which consists of adding a feed forward to the last block cipher call. And now a key committing attack on this reduces to finding a collision in the Davis-Meyer construction for the block cipher. And so if this is secure, then you have that CMAC C1, which is the scheme, is a key committing secure variant of CMAC. So now, due to the intrinsic relationship that exists between an AED and a MAC, we decided to revisit the security of generic composition, where generic composition consists of combining an encryption scheme that provides confidentiality with a MAC that provides authentication to build an authenticated encryption scheme. So the first to formally study generic composition was Bellaray and Prempeh. However, Prempeh, Rogoway, and Shrimpton later took a look at its more modern formalism, which is to build a nonce-based authenticated encryption from the combination of a MAC and an Ivy-based symmetric encryption scheme. So the main paradigms extracted from the paper are showed here with encrypt and MAC, encrypt then MAC, MAC then encrypt, and SIV. So what we want to understand here is how the committing or context discovery security of the underlying MAC or the underlying symmetric encryption scheme extends to the generic composition paradigm. For example, we would like to strengthen a non-committing symmetric encryption scheme with a committing MAC, or inversely, to strengthen a non-committing MAC with a committing symmetric encryption scheme. However, as I will now show, no key committing security can be assumed on the encryption part. So the encryption part is an Ivy-based symmetric encryption, which has the following syntax. It takes as input a key K, a variable input length message M, and an IV to return a ciphertext C. It's also invertible, meaning that with a key K, a ciphertext C, and an IV, it's possible to apply the inverse of a symmetric encryption scheme to obtain back the message M. So some example of this could be counter mode encryption or CBC mode encryption. And so a key committing attack would be here defined as finding two tuples of inputs for which the key is different and which correspond to two outputs that collide. But this is quite easy to build. So again, you can choose like arbitrary values for K, M, and IV, apply the symmetric encryption, obtain C, which is here. Then you choose a distinct key K prime from K, and an arbitrary value for IV prime, and then apply the inverse of the symmetric encryption scheme, and you obtain a value M prime. So this is then a key committing attack that is valid for any IV-based symmetric encryption scheme. So we cannot assume any key committing security on the encryption part. But what we already know is that we can build some key committing, context committing, or context discovery secure MAC. So the question now is, could we parse this property to the AED while we have no assumption on the encryption part? So for context discovery security, this is a positive result. So if the MAC is context discovery secure, then encrypted MAC, and SIV are also context discovery secure. However, for commitment security, it's a bit different. You have a negative result, which is if the MAC is key committing or context committing, then encrypt then MAC and MAC then encrypt don't inherit from these properties. So we could not assume any key commitment on the encryption part. So we looked for a weaker notion that could be assumed on this encryption. And this is what we call key robustness security, which is a bit similar than before. So you need to find two tuples of inputs for which the outputs collide. But now with the added restriction that the message and the IV should be the same here, while the key K and K prime should be different. And then we show that the main encryption mode, which are counter mode and CBC encryption mode, in fact, satisfy this property. And then as a positive result, we obtain that if the symmetric encryption mode is key robust and the MAC is context committing, then encrypt and MAC and SIV are also context committing. However, there's also some negative results, which is with the same assumption, encrypted MAC and MAC then encrypt are not context committing. So we then took a closer look at the attacks on this generic composition, and we noticed that they all use the fact that the encryption and the MAC part use two independent keys. We then wanted to prevent these attacks and then looked at a slightly modified variant of generic composition, which is generic composition with a key schedule, where now the key for the encryption and the MAC part are derived from a single key through a key schedule function. We then have the following result, which is that if the key schedule is collision resistant, then all the properties of the MAC scheme are conserved for all the paradigms except for MAC then encrypt. So the summary of analysis are showed here in this table, where the first row represents the assumption on the MAC, the second column, the assumption on the symmetric encryption scheme or the key schedule. And then the table indicates whether the security of the MAC extends to the generic composition paradigm. So as takeaway that we can have from this table is that little can be said for MAC then encrypt, which is perhaps not surprising, as the output of the MAC is not directly accessible by the adversary. For the remaining paradigms, they almost have the same behavior with a small exception, which is encrypt and MAC and SIV provides strong commitment security and context commitment security when the symmetric encryption scheme is key robust, which encrypt and MAC doesn't. So as future work that are left to be done, there's analysis of some of the remaining generic composition combinations that are left open in the previously shown table. We also believe that there's probably a lot of other practical settings requiring commitment and context discovery security that are still left to be identified. And as our analysis show, there's very few MACs that provide commitment security. And thus there's a need here to design new schemes that provide this security while being based on different underlying primitives. And finally, as it was also discussed in one of the previous talks, there's a possibility here to design a MAC schemes with beyond birthday bound committing security. Thank you all for your attention. So
Thank you very much.
Yeah.
Thank you. Any questions for Jerome? So you have all these options in the matrix on the previous slides.
Mm-hmm.
So which ones do you think are most efficient with the current constructions?
The most efficient. So it depends. So these are like generic compositions. And usually, like practical scheme don't really, that they follow this paradigm, but they use the same key. So it would be like maybe similar to one of this, like with a key schedule which are collision resistant. And then they all have the same behavior except for MAC and encrypt. So I think, well, most of the current one use encrypt and MAC, so probably encrypt and MAC would be.
Okay, there's no more questions. Let's thank Jerome again. Thank you very much. So we move to the final talk of this session, entitled Information Theoretic Security with Asymmetries. It's joint work between Tim Bane and Yulong Chen, and Yulong will give the talk.
Let's go ahead and take your badge.
Okay.
So forward, backward, laser pointer. This is a blackout key, so avoid it unless you want to block it.
Is there some way I can see the time or something?
That time,
Okay.
I'll let you know.
Okay. Okay, so thank you for the introduction. Before I start with the idea, it's actually important to explain some ideas from the hypothesis testing. Okay, so making decisions is a very important thing in the life, right? Because in the most cases, decisions are like binary. For example, do I need to accept this job offer? Do I need to continue in this research direction? Or do I need to go to vacation in the weekend? Or do I need to spend this weekend to break some rainbow construction using my laptop or something? And then depending on what your decision is, you may have big consequences. An example is like during the COVID period. Suppose that you are a doctor and then your goal is to define if this person needs to be placed in ICU or not. Then you need to make a decision between like place it in ICU or do not. And then it may have big impacts on your decision depending on this person has COVID or not. For example, yeah, in this case, there's something that calls false positive rate alpha. That actually means that suppose that there's someone with COVID, and then you decide to not put this person in ICU, then this person may die at the end. And then on the other side, if you decide to put this person in ICU, and then it turns out this person doesn't really have some big trouble, it's just like a small illness, then you may create unnecessary expense. And you can see there's a trade-off between the two type of error rates. And actually, you can control those two type of error rates by defining a threshold value T. And then you can see there's a relation between alpha and beta. That's very easy to see because suppose that assume that you are a doctor who want to accept more people to the ICU, then you can see that you actually make this alpha rates smaller because you are accepting more people. So there are less people who are going to die because they are not putting in ICU. But at the same time, the beta rate will increase because there are more people who don't need ICU will be put in ICU, and that they will create more cost. But you can see there's actually an asymmetric behavior between alpha and beta, and depending on the situation, you may choose to put one of the error rates more weights than the other. And then another important thing to note is like this area is like 1 minus beta. This actually, that's called the power of the test, which is actually the probability that you correctly reject this null hypothesis. So the null hypothesis here is like putting this person in ICU, but alternative hypothesis is like do not do that. And then therefore we can see that, so this one is correctly rejecting this null hypothesis because you are actually choose for reject, but you are in the alternative hypothesis area. Now, you may think like, what should I even care because I'm a cryptographer? And actually, it's very important for cryptographers. Suppose that you are a reviewer, then your decision here is still to make, whether you are going to accept this paper or to reject. In this case, a false positive rate is like you decide to reject this null hypothesis H0 here, then you are going to reject this paper. But it turns out it's like, an RSA paper or something like proposing of RSA. And then on the other hand, the false negative rates here is like you decide to accept this null hypothesis. So you accept this paper, but it turns out the entire paper is just wrong. So as a reviewer, you also need to make a trade-off between the two rates. Okay, done with the joke. And then here's a more serious cryptographic application. In general, like for security like indistributability, you're actually doing the same because you get two worlds. One is real and other is ideal. So actually what you are doing is like after you make several interaction with the given oracle, you need to decide which of the two worlds that you are interacting with. So we can see that the deterministic information theoretic distinguisher actually as a hypothesis between the two transcripts, the ideal or the real. So one of the worlds is chosen as the null hypothesis, and then it's your goal to decide whether you are going to reject or to accept this hypothesis. Now, traditionally, this security is measured by the statistical distance. We can actually show that it's just 1 minus the 2 error rates, but that is actually done without any justification. Now, in fact, so for almost all applications, the goal is to minimize the cost of the attack. For example, the number of queries, the time, or the data complexity. And then there's always a cost function that's related to the two type of errors. For the case of statistical distance, you can take, for example, alpha plus beta, then this cost function is minimized when alpha is equal to beta. And then, as mentioned before, from the previous examples, you can see that in practice, the two rates are usually asymmetric. And then, while in the case of statistical distance, you just assume that alpha is equal to beta. This is something that can be shown and is previously proven in other works of hypothesis testing. And then, but as mentioned before, the cost functions in practice are usually not symmetric. And then, so statistical distance actually says that whether you choose a null hypothesis as ideal world or the real world, it actually doesn't matter. But for the general situation, it actually does matter. So the goal here, the question here is like whether we can lower bounds all possible cost functions. And this work will provide a solution while by bounding this success probability of rejecting the null hypothesis in a function of the false positive rate. Now, So you may ask what's the advantage of this, using this bonding this power bond of the test. Then you actually have different cases. As mentioned before, the statistical distance is actually a subcase of the power bonds where alpha rate is equal to the beta rates. That actually means if you get security in this form, you automatically obtain the statistical distance security. While on the other hand, we also provide a new way to prove the multi-user security in a modular way without performing new analysis. And at the same time, it can also lead to other securities such as message or key recovery security. So I'm going to explain in more details. So usually multi-user security is very important, and usually how we do that is like either you just do a new analysis, but currently there are actually not so many methods that can obtain the multi-user security immediately from the single user case by without performing any security analysis. And then so this area is still unknown, but in this work we are able to do this. So suppose that we have a power bonds in the single user case, we can immediately get the multi-user power bonds. As I mentioned before, the statistical distance is a subcase of the power bonds when the two rates are equal. So that actually means you can always get the statistical distance advantage from the power bonds. That also means that you can always get the multi-user security from the multi-user power bonds. So this is actually a generic way to do that, and therefore there's no need to perform any dedicated analysis and dedicated proof anymore in the future. And so what's catch up here is like, you may think then it's probably very difficult to prove these power bonds. And that's actually not the case, because we are able to adapt the most widely used proof technique like hybrid argument or an edge coefficient technique. And we prove this in this work for three constructions: PRP, PRF, switching lemma, the Ivan-Mansur, and the soft permutation constructions. And due to the time limitation, I'm just going to explain the first one. Now, the PRP, PRF switching lemma, it's, I assume everyone knows what that is. And then the difference between two rows is just, whether the collision happens or not. So what you are going to do is like, you replace this PRF transcript distribution by another distribution excluding this ZP. And then, this power bond is, bounded by in this form. Now, B is actually a transcript where collision happens with the PRF, and this epsilon is just the collision probability. So this idea can be adapted to other construction, but you just see how it works for the PRP PRF switching lemma. Now, if we compare the results, then we can see actually there is a big difference when we choose the null hypothesis to be a PRF and when we choose the null hypothesis to be a PRP. I'm first going to explain this one. So when we choose a null hypothesis to be PRP, you can see that it's actually no advantage compared to the how we do it traditionally. The reason is 1 minus beta is the success probability to reject the null hypothesis. That actually means if you take null hypothesis as a PRP, in order to successfully reject that, then you are actually interacting with the PRF. So how can you detect that you are interacting with the PRF? Well, if you see a collision, then you are sure about that. On the other hand, if your null hypothesis is a PRF, then in order to successfully reject the null hypothesis, then that actually means that, how can you detect that you are interacting with the PRP? Well, there's actually no way you can for 100% sure that about that, because there's no event that you can see that make sure that you are interacting with PRP, because the fact that you don't see anything, then it can mean that you are interacting with PRP, or it means that you are interacting with PRF, but you haven't seen the collision yet. It's just like if I make the statement, there are no trees in the world, then you can falsify this statement immediately. Well, if I say there are no trees with rainbow color, then you are not sure that I'm 100% right or not. Maybe there are some trees somewhere that you don't know. But that's just the general idea. So if we compare this case with the traditional statistical distance advantage bonds, then we can see when this alpha rate is small, which is the case for the most of the applications, then there's actually a big difference between the success probability. Now, so as mentioned before, we can adopt different methods. Yeah, here's an example of the hybrid argument. And yeah, the idea is actually very easy. You define intermediate distribution and you use triangle inequality. Using the power bond, you actually do the same. You actually just calculate the power bonds of independent distribution P and X and Q independently, and then you put it in that way. That's just something that can be proven. And then if we apply it to a counter mode, the idea is actually also very easy. Then here, the intermediate distribution is like when I use a counter mode with PIFs. And then the first step, the F here is actually you distinguish the ideal encryption scheme from counter mode based on PIFs, and the output is always random. So there's no way to distinguish except random guessing. While if you distinguish counter mode based on PIFs and counter mode based on PRP, then this G here, yeah, this is just PRP PIF switching. So you can see this bond is actually exactly the same as before. And then where epsilon is the number of blocks. And then so what do we learn out this results? Then, as mentioned before, statistical distance is a subcase when the two rates are equal to each other. So you can always get statistical distance out of this. And then you can get multi-user security by using our proposed theorem. And the third thing is like, you can also get security bonds in other models such as message recovery. And then assume that we want to prevent message recovery attacks on the counter mode. Then suppose that there's a message that will take 2 to the power b possible values. And then the message recovery security, then here, at first we must output the list of alpha times 2 to the power b candidates for this message. In the extreme case, that alpha is equal to 2 to the power minus b, then you just output one value, then it's your candidate value. But usually in this case, you know the value of alpha, then you know how many candidate values that you can output, and then alpha value is usually very low. And then the probability that you incorrectly get this message is obviously alpha. And then on the other hand, according to what I mentioned before, then the probability this message succeeds using this error rate alpha is equal to 1 minus beta. And that's this thing for the case of counter mode. Now, so if we compare it with the traditional security using statistical distance using this alpha and this epsilon value, then we can see there's a big difference because traditionally those two terms are not really related. That actually means if you perform a message recovery attack and then we want to recover B bits of this message, then as long as this epsilon value is large enough, then it actually doesn't matter how much bits that you want to recover, then the success probability will always be super high. So whether you want to recover 4 bits or 8 bits, it's actually no difference. While if you do it using power bonds, then you can see that because the fact that you have like epsilon multiplied with 2 to the power minus b, then even if the epsilon value is very high, then your success probability is actually going to decrease if the number of bits that you want to recover becomes larger. So you can see that the more bits you want to recover, the lower this success probability, which is actually very normal. So so this talk I can only explain for the basic 2 examples, and then the more difficult examples can be found in the paper. So the catch-up is like we are able to provide power bonds instead of traditional advantage bonds, which cover the more general case when the 2 type of error rates are actually undefined or are not equal to each other. And then we provide the hybrid argument and edge coefficient technique both in the power bond model, and we applied to both PRP, PRF, and even Mansour and some of permutations. And we are able to provide methods that convert the single user security to the power user security. And then for the future researchers, for example, you can adapt other notions to the power bonds model, or adapt more other techniques, for example, that requires the expected value. And we can also recommend to prove the power bonds of constructions outside symmetric key cryptography. So this is the end of my presentation, and thank you for the attention.
Thank you very much. Any questions for you, Long? So have you encountered cases where it's difficult to switch to this model, where you tried and it turned out to be difficult?
Yeah, at this moment, I think all the constructions, yeah, you can apply it to all the constructions, but yeah, the problem is some of the constructions are proven using the proof technique that is not mentioned. Yeah, that's not those two. And then in that case, you are not able to get a very good security bounds that can be obtained using other techniques in the classical statistical distance model. So therefore, I think it's important to improve the proof techniques, but there's no really a limitation on the construction itself.
Okay, if there is no more questions, then let's thank all the speakers of this session. Thank you very much. So we now have lunch and we start again at 1:40 p.m. for the last session of Crypto 24. Heel groep al de eerste groep was in like een alpha generator.
Ja, oké. Dus dat is echt wel een formule dat we gewoon kunnen bewijzen. Dus als het 1,5